Well, thank you both very much for your time, colleagues. This is Mike Anthony from Ann Arbor. We had the pleasure of a colleague who's pretty much the first name in this type of power system. I have a very brief sort of front end type of a front end material that you can so you can understand what we're driving at. And I'm going to give the show over to Dave Shipp. So again, you will see this in the video recording we post on the education and healthcare industries facilities website. So this is just some bullet points for everyone to understand that this has always been permitted. And now that our campus power systems are growing very large, and many of them are larger than many utilities, at least many cooperative utilities, we would like to be able to approach them as mission critical systems, especially since many of them have hospitals. So there's some bullet points there. There are some advantages. Dave is going to get into the fine points of this. I've given you 2 advantages and 2 disadvantages here. And at this point, we also, Jerry Jimenez and Jim Murphy from the University of California and Lawrence Berkeley Laboratory a couple weeks ago did describe their resistance grounded system. It works well for them. They have the advantage of being in a seismic zone. And I think they also had the advantage of Dave Shipp working for Westinghouse, who installed it there. So there's a little bit of a backstory there. So with that, Dave, it's your airplane. I'm going to put us back on your image here.
Hold on 1 second, Mike.
Yeah.
In California, you were talking about California. I learned at the conference, Dave probably knows this, but apparently the California code requires healthcare facilities to be high resistance grounded. I didn't know that.
I planted that seed 30 years ago in Los Angeles, and Cedars-Sinai Hospital, to my knowledge, was the first 480-volt hospital to go high resistance grounded. So what you're telling me, they're starting to do it a whole lot, because I hadn't followed it in recent years. Let me give you an example. The pulp and paper industry about 40 years ago went to high resistance grounded. Well, they'll have 100 MVA loads like you do, but they'll have paper machines with 100 drives on it. You nooses trip one drive, it rips the paper, and it costs them $4 million, and the process goes down, and the like. And so the production issues. And so what I started doing is say, I can't think of a system in the emergency system, for example, in an operating rooms and hospitals or so forth, that have the same type of requirement that a paper machine is. A process in the paper industry, but it's life and limb in the hospital. And frankly, I don't care about the process. I care about my life if I'm on the operating table. So I started planting seeds approximately 30 years ago out there. So what you're telling me, they've actually started to do this where they're making it mandatory on the 480-volt hospital systems, at least in the emergency rooms. Is that what you're confirming to me?
That's what I heard at the IEEE conference last week, that it's now a state code, California state code, that healthcare must be high resistance grounded.
Oh, wow. I tell you what, if I go back about that same 30 years, 1971 National Electric Code, or was it the 75? Anyway, in the 70s era, and the city inspectors in Los Angeles were interpreting the code that if it didn't say you could be high resistance, they weren't letting them do it. It would only allow resistance, and that's where they started putting the exception into the code that says high impedance grounded normally resistances shall be permitted. And it was really because of the inspectors. So what that's telling me, California's come an awful long ways.
Yeah, it sure sounds like
that makes me feel really good. Well, let me go and talk a little bit about what Michael and I started looking at and doing, and we kind of started this 3-4 years ago, and to do it, say, what can we do in your setting, in the university setting, and it's driven on multiple things. One is reliability, one is what it costs you to replace it, fix it, minimize damage, the safety issue for it. And then we started going quite a bit of different settings with Michael, and we realized that there's 2 different dimensions or systems, like the 480-volt systems, like in hospitals that are typical, or the low-voltage example, mainly because more people are in close proximity than they are going to be to 15,000-volt distribution systems, or 4160, but the medium voltage levels. And really some of the requirements and the environments, the settings, and the impact on the university and so on would be quite a bit different. So we started approaching it and broke it into 2 parts. So what I want to do is we can either talk the 480 volt type systems, which is the hospital issues, like you said in California, and there's no reason you couldn't do it. You couldn't do it in any university. In fact, when it gets to the arc flash arena, I'm going to give an example that I've been trying to get people to do for probably 7 or 8 years, and it's something I feel like I'm an evangelist. I'm on a soapbox preaching the gospel, and nobody's listening.
Well, it's a culture of pushing the education facilities industry. They're not, they'll have innovation out on all the innovation shingles everywhere to get you to innovate, and then you come with an idea, and they just say their best defense is we can't afford it, and the other one is more politically oriented. So, but as you know, we've had progress. We've made success in getting the transformer size issue. I say it's been easy. It's been politically treacherous, but we have made progress. So,
that's good. That's good, Michael. I'm glad to hear that. Well, let me tell you one of the reasons, and what I'm going to do is take the high resistance grounding and or how they do it today for solid grounding at 480. And I'll do the 480 volt example because it's everywhere in the USA, but obviously if I could do it in a commercial building, I could certainly do it in a university. As long as it's above 150 volts, then you have the option. You don't have to solidly ground. But the main reason they were solidly grounding, if you go back 30, 40 years ago, is if I solidly grounded, it was cheapest. It was the safest if nobody knew anything at all, because if any ground fault you get, it'd be big smoke and fire, trip something off, blow a fuse, and take itself out of service. But it was also the worst from service continuity. It was worse. And if you're doing any service work in a cabinet cause an arc flash event, it's going to be worse. My biggest problem was with all the arc flash studies we've been doing through the last 10, 15 years before I left Eaton, was a very common hospital or a facility. They'll have a 480 volt transformer, 2000 kVA, for example, 4-wire, solid grounded, and they run 277 volt lighting. So here's a 2000 kVA transformer, and there'd be 5% of the load will be 277 volt lighting connected line to neutral. And if I have line to neutral loads, you must solidly ground to be able to supply the line to neutral loads. But then what they would do is they would, pardon? But anyway, what they would do is they'd have 277 volt lighting panels down the hallways, and then from the 80s and so on. And so when you pull the cover and change the circuit breaker for the 277 volt lightings, it'd be exposed to the line side of the panel board, and now you're at the 480 volt level right at the 2000 kVA transformer, and the arc flash has an energy so high you can't even be in the area. Because you're exposed to the line side of that breaker, and I'm saying that's really makes it an issue, and these are a lot of times just in the hallway. So that what that says is you'd have to rope the hallway off and not let anybody walk down the hallway when you're working on it, or do it at 2 a.m. in the morning or something. So I got to think, we need to change the system and design either high resistance grounding, put isolation transformers, mods. We need to use some of these to get the incident energy down real low and at the safety. Once I do the isolation transformer for, say I have 277 volt lighting, I'll do a 15 kVA delta 480 to 480 277, feed the one lighting panel, small kVA, feed the local lights locally, and then all the neutrals go away, and on the 480 volt, the utility side, and I can then high resistance ground, and I've eliminated the requirement for doing that. And they say we can't afford it. When I put it in, do you realize how much money they pay for copper to run 100% neutrals everywhere to use 5% of the capacity? And the economics actually will work out for them if they do it right up front. So I can address the safety, I can give them safety continuity, and I can borrow from these other industries and retrofit it into your setting. And see, that's what I was trying to do in the hospitals, especially in the emergency rooms, all the rest. Now, the only requirement with a little bit of engineering design.
Excuse me. Can somebody who's talking mute your phone? Mute your phone if you're talking, please. Okay, Dave, I'm sorry.
Okay, I was wondering.
Go ahead.
A little bit of design and the grounding issue, I can improve the safety, I can improve the continuity, and save money in the process just by how I judiciously put it together. And that's really the bottom line. If you worked it, I've worked through all this and scratched my head on how to solve problems like this in the past. You know, Tammy's been looking at a lot of the arc flash stuff and working on the arc flash incident energy issues. And so you know that if we go to a small kVA transformer, the incident energy goes down dramatically. And we can work around and make those things work. So what I want to do is improve the safety. Now, there's only one national code requirement that differs when I go to high resistance grounding versus the other. Well, I say there's three. If you go to the high impedance grounded part of the code, it's first of all, it's service continuity or something like that is a requirement or desirable. You cannot serve line to neutral loads, and you must have trained maintenance personnel. For example, if you open the panel bow board and you measure line to ground voltage and you think I'm going to get 277 volts, for example, but I got 480 because there's a ground fault on it with some little high voltages, you need to know how to deal with a safety issue on the voltage piece. And about 2 hours of maintenance crews, as we've retrofitted these in other industries, will meet the requirement of the code for the safety piece for the maintenance personnel. And other than that, it's done. Now, that's the concept that I've been doing, and I've been literally trying to take the industry and what I've learned in the other process industries and put it in different ones where it makes sense. And I can't think of especially research facilities and hospitals. I want to do all hospitals that way at the 480 volt level, not just the universities, but I know there's a lot of university type settings that have hospitals in them. So let's start there and to show them that we've learned a lot in the last 20, 30 years to dramatically improve it. And so that's where I was coming with it. We had some long discussions with Michael, and I guess Jim Harvey, you've been on the side discussions at times at IEEE on some of these. So these are some of the areas in where I wanted to go. Now, having said that, it's super easy to retrofit a solidly grounded system to make it high resistance as long as you meet the code requirements. I just got to make sure I get rid of all my 277 volt lighting loads or so, because I can't run. And remember, I can't run line to neutral loads if I'm other than solidly grounded. Yeah, and so there's some issues and things to do on that, but it's not super expensive.
When you start from scratch with a new hospital, we can do that. I don't think we're able to do that with the Mott Children's Hospital, but I know we've advanced the idea of, for long bulk feeders for lighting, of using step-down transformers to trap the zero sequence current, for example. But it's just design practice. You're getting the architect engineer retains an electrical engineer who may or may not be skilled in understanding. You know, you can save a lot of money not carrying the neutral, and not only that, you can start partitioning some of your arc incident energy if you do it that way. It's easier to do that in a fresh new building, and we've advanced that and had that up and kicked that idea out there. We don't always see it in bidding documents, do we, Jim? No. Okay, but it saves so much money, but they simply don't do it, and you've obviously pointed out. So again, that's why on the announcement, there's the cultural headwinds that I say that we face with some of this. So if we can bring it out, we can really increase safety and reliability if we just simply make these cultural changes, because the code permits it. So anyway, I just wanted to interject that what you're talking about in many cases is good design practice, but we're just not getting the architects to pay the electrical engineers to do good design practice. They're doing too much of what they used to do. Go ahead, Dave.
Yeah, well, Michael, you're right. They've been the most of it's the building, the architect, the practices. No, by the way, they have electrical, and they look at the initial cost, and solidly grounded is the cheapest way to do it. But the driver is, I gave up trying to educate them and talk about this because they don't want to do the math to prove that it's cheaper. What I'm using, where I'm starting to get some headway, at least in the other industries, is the incident energy one. If I do it the old way, okay, and have very high incident energies like in the lighting panels, so where more people are acting in it, less qualified. If I have a 15 kVA transformer, isolation transformer feeding that one lighting panel, the incident energy is down in the dirt. If I don't have the transformer, just do it at 480, 277, I got to have a spacesuit on, or I have to turn power on that feeder off completely just to change the feeder circuit breaker off out of the panel board in the hallways. And so the driver is going to be the safety, and that's mandated with a new OSHA laws and so on, and the incident energy issue. So I've found that I've got more headway if I approach it from the safety, and then they don't have to go do the math and prove 3 days worth of proof and math and stuff. Let's say it's cheaper to leave the neutral offers, for example. So I just found a different way to get their attention, to find their hot button. In fact, I was doing it in a pharmaceutical, and I went down the research pharmaceutical about 5 years ago in the New Jersey area, and then the research facility, every 2 feet there was another panel board running a different thing. There's probably 50 panel boards in one little bitty hall, and they all had labels, and they were mislabeled too. They said they were like category 4, and I'm looking at a 15 kVA transformer feeding it. This is when the 125 kVA rule is very dominant. And I looked at it and I says, well, whoever did your arc flash study didn't know what they were doing, but I went through a lot of the things and talking about it, what they could do, and they're looking at it. Here's what I found has happened in a lot of industries. They'll put the new stuff in, like you said, Michael, because it's straightforward, and then the maintenance people and everybody get used to it. It's so much safer and easier to work with. Then they come back and say, I want to retrofit the old stuff too. And there's ways to retrofit the old stuff very economically, but their mindset and the culture and politically correct and all the stuff that you talked about are there. So let's start with the low-hanging fruit, and after a while, they're very much in favor of doing it the other way, and then it grows over time. So that, in a nutshell, without taking all your time, is probably the low voltage example. The exception, obviously, is if I'm at 122.08 volts, I'm less than 150 volts to ground. Your only choice is solidly grounded by code requirement. Mm-hmm. But if I'm at the 480 volt level, then I don't have that limit requirement. Okay.
Yeah, I'll add to that. So I think are you going to move on to the medium voltage example?
Yeah.
Okay.
I'm ready to go to medium. We could talk all day on it, but I thought I wanted to go to you wanted to go to the medium voltage and not take all day.
Yeah. Well, I did want to make a statement about the money flow. They would rather, and this gets into the cultural issue, as you know, that our industry is very much a compliance industry. I'll get back to the innovation, all the bloviating and the posturing and the pretensions of innovation. They're really not serious about it. They're just serious about saying so. So the example I like to use is that they would rather hire 5 compliance folks for $100,000 each to go around checking incident energy labels and conformity to the code for the incident energy that exists there, rather than spend the same $500,000 to reduce the flash hazard to begin with. I'll say that another way, is that they're much more interested in conformity and compliance and have budgeted that because they understand that. The people who are in charge of that understand that. They don't understand that you can actually reduce the hazard itself. But they don't care. They don't care. They just want to conform to the rule, and they don't second guess what the rule is to begin with. And to some degree, I'll blame some of my electrical colleagues who aren't proactive, and they would rather just roll in, bill for a flash hazard study, and walk out. And they may not be saying, look, your incident energy is here too high, or you could take everything down if you did this, this, and this. So I know I'm preaching to the converted, but I did want to make a statement about the enormous cultural headwinds that we face, particularly in the education facilities industry. So with that, if anybody else has comments on that, go ahead.
Michael, Dave Shipp. You need to realize that you're not the only industry who's got that same problem.
Okay.
That's the rule.
What I'd like to remind everybody that the education facilities industry is a $300 billion industry. Just the facilities. We're a $1.2 trillion industry overall, but just laying out facilities, keeping them, building and maintaining them is $300 billion. That makes us a Fortune number 3 company. We're the largest non-residential building construction industry in the United States. And yet they still keep doing the same thing over and over and over again. So I don't want to take any more of your time. I know I'm preaching to the converted.
Well, yeah, I know. Michael and the rest of your team, and I'll just let it drop at this. One of the biggest things that I've been doing for the last 30 years is education. to educate them on how come and why for. And Tammy, I know you've been doing it with the arc flash and what you've been doing. And sometimes you have to tell them 10 times before it sinks in. The number one place, and I got some more stories that I'll tell you over a beer or so at the next conference we go to, but it generally takes an incident energy or some problem like this happen where somebody gets hurt or killed, and then suddenly they have everybody's attention, at least locally, they start doing something about it. And I've got quite a few where that's the case. Unfortunately, that's the wrong time to do it, but it's always, doing it eventually makes sense. And I'll shut up with that and let you go. If anybody has questions, I'm open to them. If not, as soon as you're through, I'd like to move to the medium voltage.
Go ahead.
Okay. Like I said, there's a big play at the 480, but most of these universities that I've seen in your large distributed campuses are going to be 15 kV, 12.47, 13.2, 13.8. I suspect on some of the bigger ones you're probably going to 25 kV because there's just so much distance. You're a small city by yourself. But the vast majority of the universities that I've been on that are spread out over campuses, I know about 15 years ago I helped design and modernize the University of Ohio in southern Ohio. And they were 12.47, probably 40 MVA of load back then, and spread around in terms of what they can do. And they were all solidly grounded with fuse switches everywhere, and trying to get them to change to start doing some things to give them more reliability. And we actually went through some of that analysis. I don't know if they actually implemented the grounding, but I wanted to go to a resistance grounding. Now, when I go to resistance grounding, remember the incident energy, and I'm not going for arc flash energy where you size it on the three-phase fault. I'm not just talking about an individual single-phase one. 70 to 80% of all faults that occur start out as a single-phase to ground arc fault event, and medium voltage is no different. It's maybe 70 to 80% of the three-phase bolted fault or the maximum available with one phase. But it's one phase. It's not three of them. Now, if you leave it on long enough, a few cycles, 0.1 seconds, something like that in a confined space, it will then escalate to a three-phase bolted fault if I don't clear it or do something. But here's the thing: if I'm solidly grounded and I got 20,000 amps of fault current available there, and say I'm bumping a 15,000 amp magnitude into this confined box, you're going to ionize all the material in it. It's going to quickly escalate into a three-phase fireball and melt everything down. And then the damage, now if it's contained in the metal box per the standards, someone's not going to get hurt as a rule unless he's got the door open. But the damage is going to be massive. You're going to be replacing it. One of the last things I did 2 years before I retired was spent 2 weeks with Boeing out in Everett, Washington, where they lost power at 13 kV and melted the whole substation down, lost two 115 MVA transformers. It cost them probably $9 or $10 million in their facility, and the 15 switches were literally melted down. 80% of the metal and stuff is just a puddle of metal at the bottom. That's the consequences of what can happen with the solidly grounded systems, and in their case, they lost their battery supply to compound it, so there's nothing that could trip. But the point is there's horrendous amounts of energy there at the 15 kV. It's the backbone of your entire power system. You lose your 15 kV distribution system or substation feeding your campus, you're dead. You may have a few emergency generators to go, but it's literally the electrical backbone of your facility. So if I get a ground fault and I have 20,000 amps of fault current, a couple hundred feet of cable to the conduit, you're not just pulling new cable. You're at $75 per foot. It's going to be $50,000 to $75,000 every time I replace a few hundred feet of cable that's burned up in the conduit or the raceways or so on. And when it fuses to the conduit, sometimes you have to replace the conduit with it. I've been into a few cases where that's been the situation. Now, on the other hand, if I resistance ground it, instead of, I can't high resistance at that level, it's too high a voltage, but I can do 400 amps, 600 amps, and if I can limit the ground fault current when I do get that fault to a few hundred amps, I allowed enough amps flow that I know where it is, I can get my protection, trip it off in, 0.1, 0.2 seconds. You go find the fault, you replace 5 feet, splice 4 or 5 feet of cable at the fault point, and you're done. And you're back in service in a few hours at most. the incident energy, just think, is proportional to I squared T, and then all the different equations that Tammy's worked up. But I start with I squared T, just so you get a reference point. It's actually, it's not a square, but it's something less than that. But the point is, it gives you a concept of where to go to. If I start with 20,000 amps squared times 0.1 seconds clearing time, that's a big number. If I go to 400 amps squared times 0.1 seconds clearing time, that's maybe, since it's a square function, or the exponent's 1.5 or something like that, the incident energy to do damage level is a mere fraction of what it is. The economic cost, the reliability, how long it takes to get you back in service, the cost to the university, or anybody. 15 kV cable today is about $75 per foot to replace it. So if I burn the shields up in the cable at 15 kV and smoke 500 feet of cable, that's a big chunk of replacement money. If I clear it very quickly and limit the energy to something much smaller, and I'm just going to the equipment cost now, I'm not looking at the people safety piece of it yet, you can dramatically reduce it. At the people standpoint, you still have to dress for the PPE requirements for the three-phase fault. That's like the standard OSHA requirements and so on. But the probability of getting the innocent energy anywhere near high like that is dramatically less if I make sure I follow procedures and I limit the ground fault current. Because if I limit it to a few hundred amps, I eliminate the escalation almost completely. In other words, it doesn't burn into the three-phase fault unless I leave it on seconds. You see the concept, and you can mathematically go back and get some empirical data to actually work through that. So I've done this, and I've looked at it in paper mills, the steel mills, and a few places in universities and other places. And at the 15 kV level, it makes a world of difference. What we're trying to do is I'm starting to do it right now offshore oil platforms at the same voltage level. And I keep telling people, I don't care what your industry is, the laws of electricity apply, whether I'm on the space station or an oil industry 8,000 feet down a hole, or I'm on a university campus, the same theories apply. Now, there's some variations, obviously, that you have to fit into your requirement, but it's certainly doable. And where I'm coming from, Michael, is that I came from the service part of the industry, not the new equipment design necessarily. I've done a lot of the new equipment design, but as a service industry, 80% of what I did is go into old systems and say, what do I got to do to fix it and modify it and change it so I can get the benefits of the new system? So I've ended up doing a lot of resistance grounded systems. I've converted a lot of high solidly grounded low voltage systems to high resistance. And I've got a lot of tricks up my sleeve and how to do that economically. The bottom line is, if we can get some of them to do it, they're going to start seeing a significant difference, and it's going to be economic on the replacement cost. It's going to address your reliability. It's going to lower your exposure risk to people for the incident energy. And ultimately, 5 years from now, it's going to cost you a lot less. But again, what do I got to do to change it and do it? Obviously, if we start off from a new design system, you could work it out. But for example, let's say you've got, say, Jim, you run the University of Michigan system. You got quite a few 13H systems around your campus, don't you?
Yeah, we're 13.2 on Central Campus and 13.8 in the hospital.
Okay, well, let's just take one of them. Let's take the hospital because it's smaller. I'm trying to go from the time I was up there 2 or 3 years ago, and my memory's not real good, but the hospital's probably got two 13.2 systems or 13.8 systems coming into the hospital, like 2 feeders, so you have redundancy, if I remember correctly, opposed to 4. Well, that means you're going to have one substation or a couple of feeders. I go to that master substation that feeds that hospital at 13.8, and instead of solidly grounding the Y connection at the utility transformer, or maybe you got a 20 MVA transformer that's 120 kV to 13.8 or so, and I'll put a 400 amp grounding resistor, 200 amp, whatever the design allows us to do, and I change my protection. I need to make sure my lightning arresters that I have through the system can handle the different grounding system, and you can do that very economically with it. Now, if you've already got digital relays, it's just reprogram the relays using it for the industrial type of setting, and you don't even have to change the relays out. And so you can do it relatively inexpensively. You just got to make sure you don't miss all the points and stuff and do that. And then you can get the high-speed clearing that because the relay is going to look at zero sequence or the ground fault current, and it's going to trip on 40 amps instead of 4,000 amps, for example. The current will never go above 400 or 600 or whatever the design is, and the damage and everything gets dramatically less. Let's look at it from your maintenance person standpoint, Jim. Let's say you're doing infrared detections, which says I got to do it hot. So you put your PPE on, you open the back cover of the switchgear, you stand back 3 feet or whatever distance into your infrared camera. Anything happens in that case, 80% of the probability says it's going to start as a single ground fault. And that's going to be a mere fraction of the energy, and you have time to get out of the way. So it's going to improve the safety. You still have to have your PPE on to do the 3-phase or whatever, but what it does, it's going to actually dramatically improve your safety for the people, too, for the few times you have to get it exposed. So there's a lot of things we've learned in the last 10 years doing arc flash incident energy studies, and the safety driver is what gets more people's attention than anything. So I'm very pleased with what Tammy's been doing in that arena to give us some real-world empirical data and models that we can actually do something with without being PhDs for every individual system. So I guess what I'm saying at the medium voltage level, there is a 50 years of track record of low-resistance grounding in North America within the process industries. All we've got to do is take what we learned there and modify it 10 or 15% and put the concept into your university campus type setting. And then you get the same benefits that the chemical plant gets.
Yeah, that's been our thesis all along. First of all, you mentioned Tammy. Tammy, do you want to add to anything that David said?
No, I don't. It's very interesting, but I like to read and think about it before I make any comments. I've been sold on medium voltage systems for a long time. I'm a little bit more hesitant about low voltage systems.
Yeah.
What I probably should do, Tammy, you're part of IEEE. Google my name on the Explorer, and some of the older papers, I've got my name on a few of them, where on the high resistance, where we've actually shown it in paper mills and the retrofit issues and stuff. So there is, several years ago we did it. But you can go read some of the papers on it, and if you can't find it, I'll dig it out of like a PDF of it and email it to you, where we've actually retrofitted to give you some of those issues so you can read it. You have to have some special training for the maintenance people, but it's 2 to 4 hours and you're done. It's not hard, but you remember, if I've got high resistance grounding and I get a ground fault, you're going to go to 480 volts line to ground, not 277 or 0. So you're not going to have many amps flow or much incident energy, but you're going to have a lot higher voltage than normal. Now it's within range that you can handle and control it, but the guy's got to know it's going to be 480, not 0 or very low. And so he's got to be able to handle the safety part of it. But rather than try to do that, I'll think about where it's at, Tammy, and what I'll do, if I can remember it, is the 2 or 3 that I wrote you several years ago or have access to. I will send that to Michael, and he can just send it out to everybody on the call. Is that okay?
Yep. One of the things that I wanted to give some context to this, and you're seeing me write it out here, does the selling and buying of entire campus power systems provide opportunities for safety and economic improvements before the system changes hands? So I'll use the example of Ohio State. They just sold this power. I believe that's where they're at. They actually sold their entire power system to some enterprise, some organization. I'm still trying to get some more information about how I did it. But when you're selling your house, very often the real estate agent will say, "Look, let's get the house ready for sale so you can get a better price for it." And of course the owner sinks some money into it. I don't know if anyone thinks like that, but here we have a chance to make a fundamental change to the safety and the economy of these power systems, and it might be something where we can put this idea in a little more context that makes it relevant to the leadership. I know that what I know of the Ohio State transaction is that it was about $250 million. And that will get any board of trustees interested. They will. It's going to be my guess that they will not involve a electrical engineer, or at least an electrical engineer that that is familiar with the fine points of other other approaches to engineering a power system. So I wanted to put that out there as something that we could give a driver and get our industry maybe a little bit more interested in carrying this in carrying this out. I know we're coming on to a time limit here, and I want to let others speak. Jim, do you have some thoughts here?
Who, me?
Yeah, like Alfred.
Got put on the spot.
Alfred E. Newman. Yeah. Well, what, me worry?
Yeah.
Anything?
I had questions before, but I didn't want to interrupt this.
Jim,
I don't have anything right now.
there is some concern. We know about this. I have. I'm glad you mentioned the California state state requirement, and that's important because very often California is on the front end of taking of moving our energy agenda farther. Sometimes they overreach, but sometimes they underreach, but they seem to be on the right trajectory. So that's always something that that executives will listen to. Well, California's doing it, and obviously Berkeley did it, and I believe you're the one that actually did this. Is that correct, David? Did you do the University of California system?
I didn't do it. I had a very significant input because I was teaching classes, and the design engineers that were doing it took my class, and I had 2 days on grounding.
Okay.
Actually, Jerry Jimenez, when he worked for Westinghouse, took the same class.
Oh, okay.
I used to teach. I spent 10 years in the Westinghouse Technical Training Center, and I taught 14 different classes with grounding and power system analysis and harmonics and a variety of things. And so I didn't actually do the UC Berkeley. I've seen their one-line system and so on, but I literally was training some of their engineers and the consultants and stuff that actually went through it and did the work.
Mm-hmm. Well, they are a Pacific Gas and Electric Power Company. You must have run into this issue. I think you can see my little red ball here. Some utilities prohibit service transformer grounding. What has been your workaround there?
Here's the problem with a power company. You're talking to the distribution part of the power company, and all they understand is solid grounding because they're normally used to feeding aerial lines, and they don't have cables. So if they get a ground fault in the line, it arcs through the air, tree limb hits it, and then the recloser opens, and then falls off, and then they close it back in, and they got new insulation called new air, and it's the cheapest in the way they do it. And what I have done is I've been hired many times through my career for the industrial or end user to go fight with the utility. And what I do is they'll have a lot of the transformers for the utility will be like Delta 69 kV, for example, to 13.2 or 15 kV class, and it'll be solidly grounded on the secondary. And if I get a ground fault on the secondary between the transformer and the service entrance to the switchgear, that ground fault is going to be single phase, it's going to be big amps, and it's going to reflect through the transformer times 1 over the square root of 3 and look like a phase-to-phase fault, and it may take 10 seconds before it clears. So they want very high amp to quickly blow fuses on the primary. This is the utility's reason for forcing it. And what I do is say, okay, I understand what you want, but in the meantime, at that voltage level, anytime they get a ground fault, which is 90% of the faults are down in the system for the end user, it costs him megabucks with cables and other issues. I want a high resistance or low resistance ground in your transformer, and we'll put protection in there. And so for all the faults down in their system, we're going to limit it to 400 amps, and that's going to protect your transformer. And then I'll put a second relay between the at the same point, looking at between the main breaker and the transformer, and if the fault's in that area, the second relay causes the switch to close, shorts out the resistor, and it goes back to solid grounding, which is what they wanted in the first place, blows their primary fuses, and I've worked around it. Mm-hmm. And I've got 3 or 4 different ways to do that, and at least I can take care of all their technical reasons.
Mm-hmm.
to protect their transformer. And a few times the industrial says, screw you, I'm buying the transformer and buying it 69 kV and I'll do what I want because you just cost me $10 million in my last outage.
Yeah, that's the argument. And they'll understand that argument, especially in campus power systems. You'd probably approach the Public Service Commission for a variance on that. So I'm glad to know the California State Public Service Commission has permitted it. We'll have to go into some research as to where, I'd like to see actually in black and white where that allowance is permitted in the state of California. But I think there's also, we have to understand, and as Jerry brought this out, there's a lot of seismic considerations, so that if you're going to have the earth beneath you moving, you're going to want to limit how much energy gets released when the earth is moving, right? So it makes sense that they would use these types of regimes in a place that's so prone to earthquakes. But as we see, we're trying to convey those practices, data center practices, paper industry practices, into the hospital, into hospitals specifically, but more generally campus power systems. Unfortunately, sometimes we need major events to cause a problem there. So what you're saying here, oops, it looks like I lost my Prezi again here. It can be subtle. One of the headwinds we also face is that when you're going from solid to ground, if you got a typical main-time main into a campus system, how do you got to, the space for the resistor is the least of your problems, but how you deal with the existing cable, for example, some of the cable may not be 133%. You have to look at the shielding and what the health, so to say, of the return back to the sensing element, back to the powerhouse. Have I missed?
That's part of the design, Michael, to work around those limitations. But you're absolutely right. But anytime you do any of these, you got to have some electrical engineering design part of it to make everything work. I haven't found one that I haven't been able to make work, but you don't just do a vacuum. So you're absolutely correct.
Yeah. Okay. The other thing here too, and people, one of the first things you learn in circuits, senior level circuits, is that phase-to-phase grounds would be difficult. You can pick up a solid ground, you can pick up three-phase fault, a good solid three-phase fault, but now you get into these in-betweeners that are 0.877 of the maximum three-phase, and you won't be able to pick up the phase-to-phase fault. I've answered this with the reply pointing out to doubters that some of the more up-to-date instrumentation would pick up early warning of a cable leakage, and if you're able to summon your electricians to do a scheduled outage, that you can save something on the order of $1 million a minute on a large university campus. You want to add some color to that statement or challenge that?
You're touching a very good point, Michael. When I had electromechanical relays, they weren't that sensitive, and so some of these other faults weren't as sensitive, and you would not catch the whole range. But with today's digital relays, you could catch almost everything. I would go to zero sequence CTs, a big donut with all three phases through it, and what I've been doing in the service industry is when you put it brand new, they'd use a 50-to-5 ratio, and I could detect a 10 amp or 15 amp ground fault, where before you couldn't detect something less than 400 or 500 amps. And that argument, what you said, was there. If I go to retrofit, I do 100-to-5 split core, so a CT around the cable, so I don't have to take 30 sets of 15 kV terminations and spend 6 months and $100,000, taking the terminations loose, moving 30-year-old cables, slipping CTs over them, and putting them back on. So there's a lot of different ways to cover that, and the new digital relays help immensely to work around that. And then there's all kinds of diagnostics that you can get into it for leakages and so on. So the problem is it's a case of too much information almost. Mm-hmm. Jim Harvey's people would be on overload if they put them everywhere. But the point is there's ways to work around that today that we did not have 20 years ago.
Just so you know, the listeners here, Dave and I did manage to get some code changes in the appendix of 70E and 70B. As we said, this is already, well, this goes back, don't you remember that? We couldn't get it in the, we could not get it in the core enforceable text, so to say, but it was a recommendation, and we did manage to point out the different scale of resistance grounding, the amount of fault current you let through for different types of high, low, and resistance grounded. So we actually, I'm getting to the point where I've forgotten the kind of code changes we've been able to make, but we have been approaching this. This seems to be the one here which energizes the compliance committee and community. Once again, I'd like to repeat, these people are just doing what they're told. They're not electrical professionals. They're not in the business of challenging the rules. They just want to make sure that the rules have been abided to. And the notion of or the possibility of reducing the hazard to begin with is not within their realm of expertise. So we find that these documents here are very visible to the facility management community, and I wanted to point out we are working there. Go ahead.
No, I just said, Michael, the thing I'm saying on that same line, you see this, and that's where I came from the service business. We've done so many arc flash studies and the issues, and you run into all these problems, and you scratch their head, and now they can't open the breaker or do anything because the incident energy is too hard or doesn't meet the requirements. And so now what do we do? And we start scratching our head and say, what can we do to modify it just so they can operate their system? And then after a while, I'm big at writing papers, and 5 years later, you start slowly getting it accepted and getting it literally into the industry. For example, I don't know if you realize it, but my name's on the patent for Eaton from 10 years ago for the maintenance switch. We called it ARMS, Arc Flash Reduction Maintenance System. That was the Eaton's name for it. But it's after 5 or 6 years with all kinds of fights, it literally would take 300 calorie 480 volt systems and put it down to under 4 calories. And it took 5 to 6 years, but it's in the code today. So you aren't going to get it in right over, Michael, but the fact that you got it in the addendum for stuff in a few years, there's a strong probability with some examples that it'll slowly work back into the other part of it once they start getting some experience.
Yeah.
Just takes time. And I know Tammy's seen that a lot when she's been involved with the incident energy and all the politics and the stuff that go on. It's not easy. Mm-hmm. I've been there watching her.
So Kane, this started out because you had some questions for the Michigan State system. Do you want to add or add anything here? Have anything to say, Kane? He might be muted, or he might have been caller number 1 that left. Okay. So it sounds to me, Dave, like this could a study for a campus power system might run maybe 160 to 320 hours, depending on what data is available. Is that fair to say? If you roll in and
how big's your system? For University of Michigan, so you're probably right. But bear in mind, it's going to be a design. So the study itself won't be as much, but you got to say, okay, once you says let's do this, then you got to go back and look at relaying, and you got to say what changes have to be made, because you're not starting with a green field. You've got campuses, you've got cables, you've got existing equipment. You're not going to throw that all away. But that's not an unreasonable estimate. But it may be on the smaller campuses, it may be half that size. Mm-hmm. To give you some idea. I guess my feeling is this. One of the things that I wanted to do, spoke to Cammy stuff at the low voltage, is we ever finally get our 2 papers written, Michael, some of those things that would be to the safety and the issues would be there, and I'd love to be able to use some examples and find one that's already, a campus that's already got it or is considering it, or maybe use it as an example of what it would take to do it. Because the real-world example, technical papers as you get it on, is what really gets people's interest. Mm-hmm. So it's not just the theory, it's the practical and what I can do to take that theory and make it work. So
we could go to the NFPA database of electrical accidents, or we could actually recruit some of the help of the safety institutes for this to get a driver.
Probably not a bad idea.
Unfortunately,
the safety.
Of course, I need somebody to help on that, and I'll float up as a jump ball to anybody on the teleconference or anybody who will be listening to the video recording. Hey, we are running on to noon, and we don't like these to run more than an hour just for technical reasons having to do with YouTube. So I'm going to let Jim and Tammy, if you have any closing statements, Any questions? Anything?
One thing is, how close are you and Mike? How close are you and Dave on that paper finishing up? Is it a way to go?
Well, we probably
The reason I'm asking is I'd like to get involved with that possibly because we got a new building starting to be designed, and having a paper written on this subject, just as you said, Dave, I might be able to force the issue. It's going to be a long road to hoe, but it's an opportunity.
Well, I have 2 papers I'm writing next year, so even though I'm retired, I'm not giving up. And I'm co-authoring them, so I don't have to write the whole thing. It just means we need to move them up the priority list. And since we have low voltage and a medium voltage, I guess the question on yours, Jim, we could use yours as a concept. Say, here's the concept, what they were doing. Here's what we would like to do or how I would change it. And you could just do a conceptual design in the paper to literally show them. That's certainly doable. That's certainly doable. And if are you, Jim? Are you offering your new system conceptually to be the guinea pig for the paper?
Well, Jim, I don't want to put you on the spot, but I guess we just did. We just needed a one line. Remember back in Fort Worth? So we can talk about that off this conference. We do have 2 papers. We do have 2 papers that are 25% condition. Jim?
Well, Jim, you know you're going to help write it.
Aye, sir.
Okay, then
I just think it's a real basic schematic design, so this is the time to jump in. The safety will go up, and the cost should not go up much, if at all. Is that correct or not?
Yeah, at the 480 volt level, it may be cheaper. Because you realize how much the code says 50% or 100% neutrals. Those are your 2 choices if I feed any 277 volt loads. I'll take all that copper and throw it away and buy a few 15 kVA isolation transformers to feed your 277 volt lighting, make all the incident energy go down, and save all your copper money. And the safety goes away. Like, for example, panel boards and halls for the lighting.
Right.
And literally, I actually went through some of this with a consultant a few years ago conceptually. At the very least, it's a break even, but it's dramatically safer.
Well, we use aluminum, of course. As you know, we use aluminum.
One comment that you made a comment. You were in a university research building, and it was like 50 panels down the corridor, or something.
It was actually pharmaceutical. It was a pharmaceutical.
Anyway, well, we design research buildings. We got to the point where each researcher wanted his lab to be on a separate panel, so somebody doing something stupid in the next door lab didn't knock him up.
Yeah, I would agree with that, Jim. I can't believe how they needed 50 panels in about 50 feet, and every square inch of the wall had a separate panel board, and 20 transformers too, feeding them. Yeah, I know. I understand exactly what you mean.
We haven't gone that ridiculous, but I mean, anyway, I just wanted to make the point why many more panels than would seem necessary are put in research buildings. But anyway.
Okay.
Well, I tell you what, I've had cases where people will hit the wrong panel board and trip me offline too. Unfortunately, when I did it one time, I shut a 7,500 horsepower down in a refinery. In about 5 minutes, there were 20 white hats in the room deciding we didn't need to do any more testing. So I'm painfully aware of that kind of setting. So,
okay.
All right.
Okay, colleagues. So we'll have this up on our website very, very, very shortly. I'll probably post it over here. And we have another, well, I'll call it general meeting. This is a breakout meeting. But I guess next Tuesday we'll have a couple. And Jim, I think you're on the bubble to just tell us what happened at the Portland conference. That's probably all we have time to talk about. So,
all right,
that's it.
Okay.
Anything else?
Thank you, Jim.
Caller number 1 came back on again. Anything from caller number 1? Caller 2, caller 3. Okay. Thank you very much. I hope everyone has a great weekend.
Yeah, Michael, we'll be in touch and see what think about what you think the next step is. What it's telling me, we got to get our papers going if you want to do anything with this, so you can start getting it accepted.
Yeah,
so we got to get off our dime and start doing something.
Yeah, the deadline. I'll pull after this call. I'll send you the drafts, the condition they're in. They're in Word. They're in IEEE format. but I believe if we're going to do them at the they're due November 15th and probably are doable. So let's try to see if we can make that deadline.
At least
all right?
one of the two.
Yeah.
We can at least do one of them and do the second one later if it's possible. But well, we can take that offline. The key thing is I've already got commitments for next year. I'm not going away with IEEE involvement. It's just that you need to make it happen fairly soon.
Okay.
And then we can carry it, because I think this could really help the industry if once you get them accepted to it.
Okay.
Okay.
Great. Thanks.
I'm done. Let me know when you want, guys. I'll wait to hear from you, Michael.
Yep. Take care.
Send me the stuff.
Got it.
Have a good weekend, everyone.
Thank you. Nice chatting with you people. It's been a pleasure.
Okay. Bye-bye. You're welcome. You're welcome again to our Tuesday call too, if you want to follow up. Okay.
Send me the link so you remind me. Okay.
Okay. Great. I'll make you a committee member. Take care.
Okay. All right. Take care. We'll see you. Bye.